Hello, my name is Roy Simpson, professor of mathematics at Kissimmee River College in Sacramento, California. And in this video, I'm going to talk about we're going to actually find the Maclaurin series expansion for f of x equals e to the x and its radius of convergence. This is a very classic example that you'll find in Calculus 2 when you're first learning about power series and you have just recently learned that about Maclaurin series and Taylor series. So just to recall really quickly, if a function has a power series expansion and if all derivatives of the function exist, then we know the function can be rewritten. Actually, maybe I should just say its Taylor polynomial expansion is going to be the summation n equals 0 to infinity of the nth derivative evaluated at the center, whatever you're expanding about, divided by the n factorial times x minus a to the nth. That is the Taylor polynomial expansion. And if we're specifically asked to find the Maclaurin series expansion for a series or for a function, it would be the summation n equals 0 to infinity. And then we're going to do the nth derivative at 0 over n factorial, and then x minus 0 to the nth. So that is the Maclaurin series expansion. Now, just to let you know, the Taylor series and the Maclaurin series expansions are not necessarily equal to the function, and that's a little bit of a caveat. There is a need to kind of talk about how can we guarantee the Maclaurin or the Taylor series are equal to their functions that they're expanded for. But right now, we're not going to concern ourselves with that. The reason why this is such an easy, fun example to use for a calc class is that all the derivatives of this function are all e to the x. So, little note, the nth derivative of that function at x is e to the x, and therefore, the nth derivative of that function at 0 is 1, e to the 0th, right? And thus, when I look at this is going to be the summation n equals 0 to infinity, right, of 1 over n factorial x to the n, or probably a better way to write this is n going from 0 to infinity of x to the n over n factorial. That is the Maclaurin series expansion for e to the x. That is e to the x as far as we know right now, and when I say we know, I mean as students. This should be somewhat, if we can somehow show what we want to eventually show, that this is equal to the summation n equals 0 to infinity, again, x to the n over n factorial, which is going to be, when you plug in 0, you get x to the 0th over 0 factorial. 0 factorial is defined to be 1, plus x to the first over 1 factorial, plus x squared over 2 factorial. So this is kind of a cool expansion because we now know we can write e to the x as a polynomial. That's pretty cool. And so when you want to evaluate e to the x, you could just plug in those values into this polynomial instead. Of course, it is an infinitely long polynomial, so that's a problem. We want to find, by the way, the radius of convergence. So to converge, we require that using the ratio test, to converge, we require that the limit using the ratio test as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, we require that's less than 1. Well, let's go ahead and take a look at this sequence, this power series here. Let me go ahead and highlight it. Okay, and the sequence that the power series is based upon is x to the n over n factorial. So we're going to let the ratio, we're going to evaluate that ratio of the n plus 1 term to the nth term. So that is going to be x to the n plus 1 over n plus 1 factorial times the reciprocal of a sub n. So that's going to be n factorial over x to the n. Right, 1 over a sub n is just the reciprocal of a sub n. And now if we clean this up, again, we want this to be less than 1. limit as n goes to infinity. Let's see, I get x to the first upstairs, and I have n factorial over n plus 1 factorial. N plus 1 factorial is the same thing as n plus 1 times n factorial. So the n factorials will cancel, and we just get this. And this is the absolute value of x, because that x does not rely upon n anymore. And we get that that limit is 0, which is definitely less than 1 always. Hence, this converges no matter what we choose for x. So that implies the radius of convergence is infinite, right? We can it'll converge no matter what we plug in for x. So what's cool about that is that this e to the x statement right here, right there, as long as we carry out that summation forever and ever and ever, we can evaluate e to the pi, it'll be exact, e to the billion pi, or anything we want. We can plug it in and it will be exact. Pretty cool.